Good morning, everybody, especially for the ones from West Coast here. I know the developers waking up at 9 o'clock isn't easy. So today I'm going to talk to you about two of the projects I'm actually personally very excited about, Tungsten and DataFrames. And really, DataFrames is about making the Spark API universally accessible to everybody, from data scientists, engineers, to statisticians. Tungsten, on the other hand, is about making Spark go even faster than it is right now and prepare Spark really for the next 5 years of architectural evolution in hardware. So how do the seemingly two different technologies or projects actually relate to each other? And I'm hoping by the end of the keynote, I'll be able to convey to you sort of the architectural insights that really connects the two. They are really two sides of the same coin in the Spark ecosystem. So you all here because you witnessed the hockey stick growth of Spark in the past 4 or 5 years since Spark started in 2009. And you have really, if you search for by any measure, Spark is enjoying sort of exponential growth. But at the same time, in the same data science space, there's another set of technologies that's also enjoying the hockey stick growth in data science for the past 5 years. If you search for the term DataFrame on Google Trends, you will actually see this curve right here. And for those of you that don't know about DataFrames, it's essentially a set of single node tools that presents basically a tabular data structure. And with APIs for relational algebra, this is like your operations like filters and joins and selects and all of that. And also mathematics and statistics functions and input-output, so how you got to be able to read data in and write data out. And over the years, the community also built a wealth of libraries on top of the single node data frames to enable a lot more functionalities than original intends to. Now, Spark data frames have really becoming the de facto standard for small data analytics. If you were nowadays go on to Coursera, Udacity to take actually a data science or data analytics class, the first thing you will learn from those classes is data frames. This is even before you learn anything about for loops in computer science. So it's pretty exciting. Now, Spark DataFrames is about taking the existing single node data frame abstraction and actually expand it to go beyond a single node into a distributed setting to leverage the power of Spark. Spark DataFrames presents an API that's very similar to the single node data frames, such as pandas or dplyr in Python and R. And as a result, it is actually very easy for existing users to just pick it up. And you probably have seen some of these examples by now throughout the theme of this conference. So how do this Spark data frames and single node data frames actually contrast with each other? This is one of the questions a lot of people might have in mind. One sort of axis you could look at this is just the amount of data this different technologies capable of presenting. So in the case of single node data frames, usually they are used to process data from the kilobyte range all the way to the gigabyte range. So a lot of the real world data is actually not that big, it's small data, and single node data frames are perfect for those. However, it's challenging to actually scale beyond that just because they're bounded by the computation power and memory usually available on a single node. Now, Spark data frames on the same axis could actually be used to process kilobytes of data all the way up to petabytes of data, just leveraging the scalability limits of Spark. And as a matter of fact, often for medium data size, such as gigabytes to terabyte range, you'll see a lot of benefits of using Spark data frames, even just on a single node, because now you can leverage multi-cores. Now, the sensational side of you might be asking, so should I be learning about Spark data frames and forget about all the single node tools, or should I be learning about single node tools, and I don't really have a big data problem? Now, I would say it's really not, the right answer to this is not about Spark versus Python and R data frames, but rather it's about Spark and Python and R data frames. And what do I mean by that? So we have actually built, in the Spark data frames project, extremely good integration with the single node data frames tools out of the box. This means you could actually take a Spark data frame and transform it directly into a single node data frame, with your usual caveats applied that the data better fit in a single machine. Or you could take a data that fit on a single machine on a small node, single node data frame and transform it into Spark data frames. Now, what benefits does this sort of approach bring with just the world that you can have both coexist and actually integrate very well with each other? First, you could actually now use Spark to parallelize a lot of their workloads that was previously not possible before, just on single node data frames, even though you're using the code that literally look the same. Second, you can now actually, because over the years, as I said in the beginning of the talk, the community have built literally thousands of libraries for single node data frames. And this covers anywhere from very good, strong visualization tools such as ggplot, matplotlib, and all of this, to single node machine learning tools, all the way to advanced statistics. And now, by being able to actually convert a Spark data frame onto a single node data frame, we actually get Spark data frames actually get exposed to all these wells of tools directly out of the box. So this is actually a very powerful combo you can use. It's not really about Spark versus existing tools, but rather how do you use Spark with existing tools to achieve what you need to do and accomplish. Now, let's take a peek beneath the API level and look at how data frames are actually executed when you actually submit a job. And before I explain that, let me sort of review how RDDs are executed in Spark. So in the case of RDDs, for those of you that have actually written Spark programs, the RDD API in Java and Scala essentially takes in a closure, or put it differently, a user-defined function to Spark. And then Spark will parallelize this function to be executed across the different nodes in the cluster. So Spark is an excellent parallelizing framework. In the case of Python, we accept also a closure, or you can call it a Lambda function in Python, and parallelize it across a cluster of Python processes. Now, this user-defined function is actually opaque to Spark, meaning Spark doesn't actually understand the semantics of what's happening in this user-defined functions. All Spark knows is some function that Spark can run and can be parallelized. And this means the room for optimization is actually smaller. Now let's take a look at data frames. In the case of data frames, internally, data frames are actually compiled in Spark into a logical plan. And what a logical plan is basically intermediate representation for the steps of computation that needs to happen. So basically, logical plan defines the semantics of computation. And logical plans are actually transformed by a relational optimizer called Catalyst. For those of you that have been following Spark closely, this is essentially the Catalyst optimizer that's initially designed to power Spark SQL. So data frames are compiled down into logical plans, and logical plans are in turn compiled by the Catalyst optimizer into actually physical execution. And then Spark essentially generates the plan to execute all of these data frame operations across the cluster. And as a matter of fact, if you look beneath the surface of all the APIs like Python and R and even Scala and Java, you realize they are really just simple wrappers around logical plans. Now, this approach is actually very different from how all the other existing data frame implementations out there are built. And they actually bring us quite a bit of benefits. The first benefit is it provides much simpler front end. And front end here, I don't mean your JavaScript, but actually the language front end, meaning the bindings and APIs we can provide in other programming languages beyond Scala and Java. In the case of Python, we actually implemented the entire data frame front end for Python in about 2,000 lines of code over the course of the weekend. In the case of R, we did it in a similar fashion, except with even less code, in about 1,000 lines of code. So this really means it's now much easier because all these APIs are really just wrappers around the existing, more complicated beats under the hood. So the presented facade is actually a lot simpler. So it is ridiculously easy to actually build new language front ends. So in a way, I wouldn't be surprised if the community is building Julia, Clojure, and all the other different, your favorite programming languages here, just popping up in the next couple of years. Now, the other part about the benefits of the data frame logical plan approach is about performance. So when you are usually using RDDs, often if the Python user comes on board to Spark, Python is their primary programming language. They learn about the elegant API of Spark and RDDs. However, they soon realize the Python PySpark performance is actually quite a bit slower than the JVM counterparts. And this is sort of out of our control because Python sort of natively executes slower than the JVM. Now, in the case of data frame approaches, because all the programming languages are really just compiling down the data frame API down into logical plan and going through the same optimization path, you actually get performance parity across all the programming languages. So enough about DataFrame. What about Tungsten? The title is really from DataFrames to Tungsten. How do they actually relate? Now, let's take a look at actually what Tungsten is before we go into how they relate to each other. And in order to take a look at what Tungsten is and explain the Tungsten effort, let's take a look at the hardware trends along 3 dimensions: storage, network, and CPU. Now, back in 2010, when Spark was first started, most of the world were running on spinning disks. Each spinning disk can probably get you about 50 to 100 megabyte per second sequential throughput. Networks were predominantly 1 gig network. Sometimes you might even get 100 meg networks. The CPU frequency was about 3 gigahertz. Now, fast forward 5 years. In 2015, majority of the new server configurations are now actually running on solid-state drives, in which a single solid-state drive can get you 500 megabytes per second of sequential throughput easily. There are ones that go up to gigabytes per second. As a matter of fact, if you were using Amazon EC2, you have to try really hard today to actually find a configuration VM that doesn't actually back by SSDs. Network, 10 gig network is becoming more and more popular. And it's basically the standard configuration now on all the high-end nodes on EC2 and all the other cloud providers. CPUs actually, surprisingly, hasn't changed that much. So in case you haven't been paying attention in the last 5 years, storage and network both increased the throughput by almost 10-fold, where CPU's frequency and CPU development kind of plateaued. Now, in the beginning of Spark, in the past couple of years, especially when we're doing a SOAR benchmark, we actually spent substantial effort in Spark to optimize for storage and network. So this is to make Spark jobs actually run much faster, given the limited storage and the network bandwidth that's available. Now, due to sort of this confluence of both our optimizations and the hardware trends shifting, now we're seeing if you run a Spark job in 2015 on the 2015 configurations, you actually realize a lot of the Spark jobs are now CPU bound instead of network or storage bound. So this is what Project Tungsten is. Project Tungsten is about substantially actually speed up Spark execution by optimizing for CPU through 3 different components: runtime code generation, much better cache locality, and off-heat memory management. Now, this is only the beginning. The whole theme of Tungsten is we want to prepare Spark for the next 5 years of hardware evolution, and actually covering even newer hardwares, which I'll talk about at the end. So how does DataFrame actually relate to Tungsten? The reason DataFrames and Tungsten, I'm talking about both of them at the same time, is because in DataFrames, we have different programming language APIs that compile down to the logical plan, which really defines the semantics of computation to Spark. Now, because Spark knows more about the semantics of computation than the RDD approach, which is mostly opaque closures, now we could actually let Tungsten generate much more efficient code based on underlying hardware, as well as Spark, the semantics of computation, the logical plan themselves. So really, logical plans and DataFrames actually enables Tungsten under the hood. That's why they're actually 2 sides of the same coin. Now, I'm not going to go into sort of the details of all the steps, because we actually have a talk going to be given by Josh Rosen at 5 o'clock today on Project Tungsten. I encourage you to check that out if you're interested about sort of how Spark might evolve in the future. But I will give you a sort of a sneak preview of what we are seeing. So we've been working on Tungsten for about 3 months with the community. This is sort of the benchmark that we run on the workload from our customers. As you can see, in some cases, so the darker green line is the with running Spark with Tungsten mode off. So this is like basic pre-existing Spark. And the lighter green line is essentially running with Tungsten on. You can see, as you can see, in some cases, Tungsten is actually able to get Spark workloads to run 10 times faster. And this is running on a real customer workload. So the early results are extremely encouraging. And as we all know already, Spark's pretty fast already. And what's going to happen is Spark will get a hell lot faster. So this is where I see sort of Spark going. At the API level, there will be different language frontends that's very lightweight, which means they're very easy to maintain, very less likely to have bugs. And with all these language frontends, they get compiled down to the common abstraction that's called DataFrames, which in turn get compiled down to intermediate representation called logical plan. And this logical plan will be compiled down through the Catalyst optimizer into different Tungsten modes that's actually optimized for the computation as well as the underlying hardware. In nowadays, most of the Spark execution actually runs in a JVM, but there's newer compiler technologies such as LLVM that we could actually exploit in certain scenarios that might get us actually substantial benefits over the JVM execution. There are also cases, GPUs are becoming increasingly popular. It's very likely they will be able to exploit GPUs for the wide parallelism that's possible from GPUs. And there's also non-volatile memory that can be used. They actually substantially expand the memory capabilities of the current hardware. So one unified API in the front, intermediate representation, and different execution backends that can be automatically optimized by it. Now, Spark SQL, the Python API and R API is already building on top of DataFrame abstraction. ML pipeline API, for those of you that know more about machine learning, is also building on top of DataFrame abstraction. Streaming DataFrame is also coming in the future. So all of Spark will be building on top of this common abstraction that in turn actually compiled and backed by the Tungsten backend. So really the goal here is Spark API should get simpler, even simpler to use, and the backend should run even faster for your existing workloads. So that sort of concludes my talk. But before I walk off stage, just want to announce we have more office hours today with Spark committers at the Databricks booth. So this is sort of the breakdown of different topics. And you're really getting a real treat today at the very end. That Matei Zaharia, the creator of Spark, will also be there to actually keep you stay at the conference until 6 o'clock. So thank you.